Okay, it's noontime now. We'll get started, okay? And last time we talked about the big X, big Y method to calculate the coordinate after rotation and translation, okay? And we also discussed the relationship between the object motion and the coordinate rotation, okay? We'll talk about that. So your object motion and is a reverse of the coordinate rotation. Okay, it's actually object, but it's okay. You just use a minus theta or minus displacement. You will be able to get the right coordinate for you. So that's the way we set up the calculation for the coordinates. Okay, that's the way we set up the discussion for the coordinates. And today, I'm going to continue to talk about the use of these different metric and vectors. So how to use your linear algebra into the modeling of the robotic spaces. Okay, but we are going back to the slices. But again, I'm not trying to teach you the whole thing. I'm trying to just to go over the key idea that help you to understand the material. Okay. So if you have no question, I'm going to get started. If you have question, let me know, okay? Let me know in the middle. So today we continue to work on this one. The lecture 3, we actually talk about kinematic diagram and representation of orientation. We talked about it last time. Okay, we talked about it last time. So here we are going to talk about this definition of this. Okay, so Cartesian coordination, usually we describe the location of an object using the Cartesian coordination using XYZ. Okay, but sometimes you can use the polar system or complex domain. Okay, it's okay, but here primarily we are using the Cartesian coordinate. So the 3 equivalent geometrical meaning of rotational metric are explained. Okay, we'll talk about it. Kinematic diagram. So kinematics is a branch of the mechanics concerned with the motion of objects. So basically it's Newtonian physics, okay? Starting from your F equals ma, okay? That's the Newtonian physics. F equals ma, and all kind of the mechanics talk about is a kinematic, okay? How things move, at what speed, and how far it travel, okay? That's called the kinematics. So here, let's just have the basic idea of what they are. And then representation of the orientation. Now, there's a word called orientation, okay? Orientation. This word is not rotation, it's not translation, it's called orientation. Orientation means the direction. So let's see, here you do have, let's assume that we do have XYZ. Let's use the right-hand rule, okay? So let's use the right-hand rule. Let me actually change it a little bit. Okay, let's assume that we do have the right-hand rule. So this is one orientation. So X, Y, Z, we do have one orientation. This is one orientation. There's another one. Let's assume that your X is this direction, right? And your Y is this direction, and your Z is this direction. This is another orientation. So orientation, this word in here, even though you are the same XYZ, but orientation means that the angle or the direction that you have in the space. So let me show you with my hand, okay? So let me stop sharing, and let me use this one. So here again, I have my hand, right? So right now, if we do have the right-hand rule, X, Y, and Z, okay, so this one is X, this is Y, and this is Z. So this is one orientation, but if we change to this angle, that's another orientation. This is another orientation. So orientation really means that in the whole space, same coordinate, you still have the difference of where they are facing. Okay, this is called orientation. So that's the idea of orientation. Hi, Nick, how are you? Hello.
I'm doing good. How are you?
So even though we do have the XYG, okay, we do have the XYG, but this XYG because of the rotation, it may have different orientation. That's still something we need to study. So they are translation. We talk about that your frame may move. They are rotation. Your frame may actually do rotate, right? Your frame may rotate. Besides that, you still have the orientation problem for your frame. So there are several things in combination to have an accurate description of your metric and things. Okay, so direct kinematic, including the homogeneous transformation. This one we would do that later. Okay, then it'll be Hardenberg convention. This one's next week. Okay, this one's next week. So okay, so these we are going to talk about this direct kinematic. Direct kinematic is to describe where your sense is. Okay, so there's an inverse kinematic. Inverse kinematic is okay. You do have some your kinematic is you do have your F equals ma, and then your acceleration, your speed make the sense move for how far, and your new location is what. That's called kinematic. If you starting from where you should be, reverse talking about how much force you need to take. That's inverse of the kinematic. Okay, so basically this one is actually just a term. Okay, degree of freedom. Next one is degree of freedom. That time we talk about rigid body and the soft body. Okay, rigid body means that you do not have scaling, you do not have skewing. Okay, so far all of the object we are assuming rigid body is not soft body. Soft body you do have some factors such as scaling, swollen. Okay, you will make bigger or smaller, shrinking or growing, and you may have tilting or skewing. Okay, so that's the difference between rigid body and soft body. At this moment, we are assuming everything is rigid. Okay, and then configuration. Configuration is special specification of the position of a point of the robot. So your location of your robot, say this one here is one configuration. So every configuration space is called the space of all configuration. That's called C space. Okay, that's called C space. So C space means that the space of all possible configurations. So configuration means that your robot may have a combination of these, may have a combination of these. If you have two fifth section of the arm, okay, it can be these or these. Okay, but anyway, whatever combination that's possible using your robot is called a configuration, and the combination of all possible configuration, we call it a C space, configuration space. Okay, so configuration space is okay. Configuration space means that based on your hand, what kind of the so I have a hand. Let's assume that this is a robot arm. So whatever sense that I can do, this is called configuration space. Okay, but there's another thing called workspace. Workspace just means that my fingertip, for example, this is endpoint. Wherever it can touch or move, that's called workspace. So these two terms are different. These two terms are different. Configuration space means that it's the combination of your arm finger condition. That's called configuration. Where your fingertip or your clip can move, your endpoint can go to. That one is called workspace. So workspace is where you can work, where you can work. Okay, and configuration space, C space, is where your configuration can be configured to. Does that make sense? These two are different. Okay, these two by definition are a little bit different. I think is that okay?
Yeah.
So configuration space means that how can you program the robot? Okay, which angle, which arm, where you should put your arm at. That's called configuration. How you bend your arm, that's actually configuration. But your endpoint, where your endpoint can reach, that's called workspace, okay? And the degree of freedom is a dimension of the configuration space. We call it degree of freedom. So degree of freedom, say we do have 1 theta, 2 theta. Okay, so this is degree of freedom is 2. Okay, this degree of freedom is 2. Okay, but this one we call it degree of freedom is 2. Okay, so say right here we do have this is a workspace. Okay, this is workspace. Let's assume that we do have a robot arm. The robot arm section 1 is here. So this one actually section 1 is here. And let's actually have a C section here. Okay, let's have a section here. So this is a section 2 actually going from here to here, and it can move 360 degrees. Okay, so using this 2-section robot, you can reach the space of a donut shape. So this donut shape is the workspace. And the possible angle, that's actually the theta 1 here, and the theta 2 here. Say here you have theta 2. So this is theta 1 and theta 2. These two combinations is called the configuration space. Is that okay? Hello? Okay. Remember this term. So this one is a surface of donut, and it's a degree of freedom 2. This is degree of freedom 2. Okay. If you including the solid middle, say you do have this, you do have the arm, but this one actually is extendable. Okay, then you may have a degree of freedom of 3 because you have theta 1, you have a second number theta 2, you may have another one displacement 1, and so that's actually become a degree of freedom 3. Okay, let me take a question from chat. Okay, Jay, okay, no problem. Okay, so that's a degree of freedom 3. So a point, an object, an airplane. So many of you are actually from the aero engineering department of the Louis. Okay, Louis is famous for it. They are a object in a space can have a degree of freedom of 6, right? You do have SYG. Where your airplane is, that actually you do have your airplane go somewhere, you do have the SYD. So you are keeping this location. So the location move from here to here, that's actually described as SYG. But in addition to SYG, your airplane is right here. You may do pitch. Pitch is rotation along y-axis. Roll is rotation along the x-axis. Yao is actually the rotation along z-axis. So basically, you will have a degree of freedom of 6, even though your airplane is a rigid body. So, but that because of your location, the position of your or location of your airplane, they are SYG, and then your orientation of this object, another degree of freedom of 3, because you have the pitch, roll, and yaw. Actually, you have another 3 degree of freedom. Is that okay? So degree of freedom is also the number of the variables. It's also the number of variables. So sometimes when we say degree of freedom, say if we are 3D, right? 3D, let's assume that we do have a 3D space. We do have a 3D space. So if there is no constraint, no constraints, then your 3D, the degree of freedom would be 3, right? Is 3. But if you do have an equation that's sy plus g, s plus y plus g equals 1, then you actually already limit yourself on a certain plane. So 1, you can only move on this plane. And then degree of freedom become 2 only, because you have to satisfy this constraint equation. Okay, if you have two equation, 2s plus y plus g equals 7. Okay, very simple. Then you have second plane. Then this is the second plane and first plane have an intersection. So there's a certain line on this space. So your degree of freedom dropped down to only one degree of freedom is only on the line. So degree of freedom also actually describing how much free running variable is needed to describe your space. Okay, so here we talk about the configuration space, workspace, and the degree of freedom. Degree of freedom deciding how much variable you should use. Okay, and then you do have prismatic join, you have the extender, you have revolute join. Okay, there's a third type called spherical join. Spherical join is like this. You can do a spherical movement. Okay, so it actually is more flexible than revolute. Revolute is the 2D rotation. Okay, and this one is like 3D. Okay, 3D. But it actually, when you draw the workspace, it's not really 3D. It actually is a sphere. It's only 2D. Okay, it still is only a surface that its endpoint can go to, unless that is extendable. If it's also spherical and also prismatical, then it will become a 3D joint. Okay, is that okay so far? Okay, so these are the joint. Usually we see this different kind of joint, but in this course, we primarily working on the prismatic and the revolute. Okay, this one a little bit more complicated. Need harder math to describe it. Okay, whatever this is okay. And then here we talk about the possible joint. I don't go into the detail. They are Cartesian joint, cylindrical joint, planar joint, whatever you can study. Okay. Here tell you the 6 dimension, 6 degree of freedom joint. You have X, Y, Z, and then R, X, R, Y, R, G. Okay, R, X, R, Y, G is your pitch, roll, and yaw. Okay, whatever. And then, okay, you can look at the name of each kind of joint. Okay, we don't repeat that. Okay, you can study it. Pose of a rigid body. So pose of a rigid body, we call it a position. So your position is XYZ, you have a coordinate. Okay, that's actually position. Okay, orientation. Orientation is that even you are at the same location, because of your coordinate may change, then your rigid body may end up with different number. That's called orientation. Okay, that's called orientation. So let's assume that actually right here. Okay, let's assume that right here, we do have a 3-dimensional space. Okay, so we do have X, Y, Z like this. Okay, and there's a point over here, and this point actually is like this. Okay, it's over here. Okay, so it's X is over here, it's Y is over here, it's Z is over here, right? So you do have a pink color of the coordinate, X, Y, Z. Okay, but if we change this coordinate to be X in this direction, Y in this direction, and Z in this direction, then you will get another coordinate that's actually using X prime, Y prime, G prime. So X prime, Y prime, G prime is the same point, different coordinates. You get different value, and this one is actually the orientation change, and this orientation change is similar to. It actually is also similar to what? Similar to your rotation. So you will get a new set of the XYZ, big X, big Y, big Z. Is that okay? Hello, is that okay? Even just the orientation of your coordinate different, you will get different coordinate. Okay, you'll get different coordinate. This is called orientation. So when you model the point and the movement of some object, you need to take consideration of the orientation, rotation, and translation. everything in combination, okay? Everything in combination to get it, okay? You need to have everything in combination to get it. So you need to not only rotation, not only translation, but there's another one called orientation. Orientation is the direction of your frame, okay, of your frame. And then there's and that luckily enough, the orientation you can also use the rotational metric to describe it. Okay, lucky enough, the orientation, so you can describe it for the rotation and also for the orientation. Okay, so let's look at a simple example on this orientation. Okay, so let's assume that, okay, here, let's use the example we just had a moment ago. So let's assume that here we do have XYZ. Okay, we do have XYZ. So here I do have a pink coordinate based on this XYZ. Okay, there is a point called XYZ. Okay, and this one is based on a black color frame. I'm sorry, it's based on a black color frame. It's used black color frame, okay, XYZ. So let's call this one F0. Okay, let's assume that the same location, we do use this one as X, do use this one as Y. Okay, so this one, let's see. No, let's pick this one as Y. Okay, pick this one as Y. So S and Y change, and your G will go to this direction. Okay, your G will go to this direction. So we do have a new system that's using XYZ. Okay, it's still following the right-hand rule. So this one, the same location, you have a new coordinate that's actually called XYZ. Okay, so apparently your XYZ compared to your original XYZ. Okay, so your big G, your big X, okay, your big X, your new X, okay. Okay, your new X will be your older Y. You'll be older Y, so 0, 1, 0. Okay, your new X is your new original Y. So this one times this one, your big X should be your original Y. Your new Y will be your original X. So you are 1, 0, 0. Okay. And your new G should be your minus G. So you have minus 1 over here. So you do get this one. Okay. So this one is your orientation metric from your original to your new one. Is that okay? Let's actually put a dot in the middle. Say this is a O. This is your orientation metric. The reverse operation of it is actually, if you want to find your XYZ based on your big X, big Y, big G, will be equal your X, your older X is your new Y. Your oldest is your new Y, so it's actually 0, 1, 0. Your new your older Y is your big X, so here you have 1, 0, 0. Okay. Your G is your minus G. Okay, so you have 0, 0, 1. Lucky enough, this one is the same. Okay. Any question? So this one is when you need to adjust for the orientation, you can still use your rotational metric to calculate it. Okay, so In some of the homework, you may need that. Okay, in some of the homework, you may need that. Any questions so far? Let me try not to push it for too hard. Okay. Any questions so far? No question? Okay. No question. I'm going to go continue. Okay. I'm going to continue if no question. Okay. Thank you. Okay. So basically, we can see that orientation and rotation can all be described by the rotational matrix. So don't worry about orientation, but you do need to consider your new coordinate system. So basically, when you have a frame here, you are using XYZ, right? Then if you have a new frame that's coming to here, there's a translation difference. And then this one may also suffer the rotation using theta. So that is actually one rotational metric that you need to do. But in addition to that, because your assignment of the frame one may have a new set of XYZ. Okay, so the orientation of frame 0 may not be the same as the orientation of frame 1. You still need to consider that in. So when you do the rotational metric, each level you need to actually consider not only the rotational metric but also the orientation. Okay, also the orientation. Okay, so this is mathematical. When R transpose times R equals identity, then your transpose is your reverse operation. Usually rotational metric, okay, because you rotate for theta, your transpose may rotate back. Okay, that usually is your reverse operation. Usually that's okay. So here, this one, usually just rotation, usually is this one may hold. Okay, so next one, you do have a roll, yaw, and the pitch. Okay, it's showing you how the airplane shake. Okay, shake, but the position may not change. Okay, your XYZ where you are, no change, but your airplane may take any roll. Okay, any roll pitch. Okay. Okay, so now two-dimensional rotation based on the XYZ. So basically right here, let's look at this one. Your Z actually no change. Okay, so you do have XYZ if you have original data here. So the last line, your Z is no change. You take the same Z, right? Your XY would actually work on this two-dimensional rotational metric with alpha angle. Okay, with alpha angle. So alpha angle is your yaw. That's a rotation based on your Z axis. So based on your Z axis means that you rotate based on your SY and Z. Your Z no change because you're rotating this angle. Okay, but the rotational metric of Z, this one is your yaw. Actually, it is described in this way. So similarly, your rotational metric for the airplane to be in beta. Your beta, this one, beta angle, your Y no change. Your X and Z change, okay? And the next one, you do have the X axis roll. Your X no change, your Y and Z change, okay? So you can see the 3D operation is based on the 2D rotational metric. Okay, so here we describe it. These are the 3D rotation, but it is just the your airplane's local position. Okay, it's not really the path that it travel. Okay, it has nothing to do with the path it travel. Actually, you travel like flying like this one, but the airplane may be this way, maybe this way, maybe facing down. Okay, so they are different way. We are describing the local things. And in the middle, your airplane may take a rotation, okay, in the middle, but your path XYZ 3D still described in this line, okay. Okay, so that's that. That's actually this 3 rotations, okay. So representation of a vector, you are using the XYZ to represent it, okay. So this one, you can have XYZ, okay. S prime equals this, okay, whatever this is, okay. And rotational metric, your P equals rotation times this, okay. You can use the rotational metric times your vector, you get a new vector, okay. This one we described it already. This is called transformation metric, okay. So transformation metric actually can be applied to your XYZ movement, okay. Okay, whatever this is, okay. 2D rotation, we covered it already, okay. So 2D rotation, we covered it already. Let's actually move a little bit faster. We don't repeat it, okay. Okay, so big X, big Y measure, we talk about it, okay. This one, we talk about it already. And next one is orientation. So let's assume that next one, we are going to talk about the composition of rotational metric. Luckily enough is that if you take several rotation at different joint, the rotational metric can be multiplied. That's good enough, okay? So basically, that's given a 3 rotated frame, 0, 1, 2, okay, 0, 1, 2. So let's assume that we have a frame 0. That one has a base spread rotation here, okay? And going up here, you have a second one. You do have rotation C that one here, okay? That's a frame 2. You have another one here, frame 3, okay? You do rotation here. Let's don't consider the displacement yet, okay? Just look at the theta. Just look at the theta, so you actually will have the rotational metric. Okay, this 1, 2 is the observation of the frame 1 based on frame 2. Observation of frame 0 based on frame 1. Observation of frame 0 based on frame 2, okay? So observation of frame 0 based on frame 2 is equal to observation of the frame 1 based on frame 2 times observation of frame 0 based on frame 1. Okay, this is combined, okay? So that's actually go lower, okay? So this one, it holds, okay? This is so. Rotation with respect to the current frame, rotational frame 0 based on frame 2 equal rotation of 0, 1, and 1 over 2, okay? Okay, that's assume that there is no displacement at the moment, okay? No displacement at the moment. This relationship will hold, okay? This Euler angle is too much, okay? Let's don't talk about it. Okay, and then you have different rotational angle, and you need to use a metric operation to time them together. It's too complicated, so we don't go into the detail. And there's an inverse problem. This is so far too hard. Okay, let's actually don't think about it right now. It's too hard. Okay, later we do have some homework to work on it. 4 parameter representation. Okay, this one I think is too hard right now. Okay, we'll talk about this one later. Okay, so you do modeling. This one we cover it already. Okay, this one cover it already. Okay, let's look at the other one. So this one, okay. Let's look at the rotational metric here, okay? The lecture 4, direct kinematic, okay? So here we are going to talk about the combination of the rotation and the displacement, okay? So before that, we do look into the rotation and the translation separately, okay? So the rotation in 2 dimensions, we talk about it here, okay? So you do have X and Y, okay? Your frame actually move from here to here, okay? So this one, your new friend 1, you do rotation, if you rotate with theta, okay? So your original point is over here. Your point right here is actually SY, and this guy is actually cosine phi, sine phi, okay, times R, okay. And then your friend rotate by theta, but your real new coordinate, this one, you become R cosine phi minus theta. Okay, we talked about it before, okay? R sine phi minus theta. Okay, and we can use the rotational metric to calculate it, okay? So that one is rotation. But when we talk about translation, you do have XY, okay? Your frame move from here to here, you do have a translation. It moved by AB. Okay, then your new X, new Y would be, let's use pink color. Your new X, new Y would be your OX minus A and OY minus B. So this one is using the arithmetic plus minus. Okay, this one is using rotational metric. So displacement, okay, and the rotation, translation and rotation right now is in two systems. One using vector addition, subtraction. The other one using the metric multiplication, okay? So these two are not in one system. These two are not in one system. So when we really work on the mathematical operation, it's going to be a problem, okay? So it's going to be a problem. So because we want to solve the problem, so we invented this one called homogeneous representation. Homogeneous means one same kind. Homo, unit, one, okay, only one. Genius, kind, okay. Gene, okay, one kind. Heterogeneous means that hybrid, many kinds. Here is only one kind, okay. You do poker, you have 4 of the kind, okay. So that actually is homogeneous representation, one kind. What kind? Metric, okay. Metric is the homogeneous. We actually no longer use the addition. If we convert everything representation into only one kind of metric, we call it homogeneous representation. Hardenberg metric is one kind of homogeneous representation. So this homogeneous representation is very, 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 very important. Okay. Before the homogeneous representation, you are using the regular rotational metric and dispersion vector. Okay, these are separate, two kinds. It's a mixed representation. Now we are going to talk about homogeneous representation. Then we mix them into one kind. Okay, so we say that composition of homogeneous transformation to derive the direct kinematic equation of open chain manipulator. So the purpose is right here. We are going to use one representation to show you how the direct kinematic equation can be formulated using only one representation. That's the main objective of this lecture, okay? Okay, so direct kinematic equation is computed for a number of typical manufacturer structure, and we are using the HTM, okay? HTM, sometimes I use HTM, homogeneous transformation metric, okay? HTM, okay? Homogeneous transformation metric, okay? And later we do have a Hardenberg representation. That's actually is one kind of HTM. So homogeneous coordinate. Before we go into the homogeneous representation, let's look at homogeneous coordinate. So homogeneous coordinate your SY, you can scale with a new number called W. Okay, W. So you have, originally you have XY. Let's assume that we do have 2D. So 2D, you do have a XY. Now let's change this 2D into 3D that has XY and the W. So W is an introduced variable. Okay, so your 2D XY will be represented by the 3D. So this 3D, we use XY equals X divided by W. So W is a number. And if we have a W equals 1, if the W equals 1, then your 2D representation have a direct mapping to the 3D representation. Any question? Any question? Okay, and why we do that? Okay, we'll show you. Okay. Okay, and for instance, point in Cartesian 1, 2, you can make it as 1, 2, 1. So there's an added variable W, we use 1. And because W is 1, so your X divided by W is your new X is still 1, 1. Okay, since everybody is 1. Okay, your Y divided by W, W is 1, Y is 2. Okay, this big Y is also 2, so this one is the same. Okay, so don't worry, we actually using the W only put the 1 there. It's not a big problem. But anyway, this one can convert your original XY to a new 3-dimensional coordinate. Okay, after that, what is the benefit? Okay, we need to look at the benefit. The benefit of it, that's actually omit this one. Okay, you can do W equals 3, W equals 6, W 6, 12. Okay, we don't care. Okay, let's actually look at the benefit. The benefit is original point. I use the XY to describe it. Now I use the XY1. When W equals 1, we are getting this one. Okay, we are getting this one. So let's look at the translation. Let's directly jump to translation. So jump to translation, we do have this one, we describe as this one is this, okay? So let's assume that this one is a translation. So your original point is located at SY, and this object moved by AB, so it go from here to AB. So the new location will be S plus A, Y plus B. And this is your new coordinate, big X and big Y. Okay, we got it. Okay, so this is the equation you have. Mathematically, it's formulated in this way. Okay, it's formulated in this way. Then we want to use the metric operation to achieve it. So let's see. Here you do have 1, 0, 0, 1, 0, 0, 1. Okay, so here this is identity metric, and then A and B, and you put your X, Y, and the 1 here. So this 1 is dummy, but it has some effect. Okay, this one is your new big X and big Y. Okay, and a G. Okay, whatever G it is, we don't care about the G. So now let's actually multiply. So this one multiply with this one. Okay, so basically your new X would be equals what? X plus A. Your new Y would be equals Y plus B. Your new Z would be equals 1, no change. So this one you will get big X, big Y, and 1. Is that okay? So all the P and your P prime can be calculated for translation using such a homogeneous transformation matrix. So you no longer using vector addition. You use a metric, and that metric is using this S metric for translation. Any question? Hello, Nick, are you okay?
I think I'm okay.
Can you understand this one?
Yeah, I think I get it.
Okay, the basic idea is that originally the operation is vector addition. Now you use the HTM, the homogeneous transformation matrix, so the translation become a matrix operation and still performing the same thing. Okay, we are talking about the benefit of doing this later. Okay, let's look at the rotation. The rotation similar. Here our rotation mathematical equation is like this. Okay, we can calculate it. Last time we derived it. Okay, there's no problem. So now let's look at it. Here we do have the new x, new y, and the z, okay, will be equal to this cosine theta. Sometimes I use a c theta, okay, minus s theta cosine theta, okay. Sometimes c theta means the cosine theta, okay, because it's shorter. So here 0, 0, 1, and then 0, 0, 1, okay. And then you have your original x, y, z. You do multiplication, let's use a green color. You do multiplication times this one. So your x times cosine theta minus your y times sine theta. Right? And this one is 1. Okay, this one is 1. This one actually is 1. Okay. What do you get? You get this equation here, your new x. Same thing for y. Y you will actually new y will get this equation using this matrix. So basically, this one rotation, you put your rotational matrix over here. You put 0, 0, 0, 0, 1. Okay. Is that okay? So basically, when you do rotation, you put your rotational matrix on the first two here. Okay. You do translation, you put your displacement over here and put the identical matrix over here. Okay, you do scaling. Scaling, you actually do SX, SY here. So your original XY1, this one will get your equation for scaling here. So anyway, this homogeneous transformation can combine scaling, translation, and rotation together. Everybody become a matrix operation. Is that okay? Is that okay? Any question? No question? Okay, the benefit of this is, okay, the benefit of this is, let's actually look at it. Here, let's assume that we do have a object, right? It actually do travel. Okay, let's actually do rotation. Okay, this object do rotation and then travels for some distance. So you can combine this one, put it here. You have an A, B, you put here. You actually combine the two together so you can use the rotation and translation in one matrix. That's the benefit. That is real benefit for it. Is that okay? Okay, so this one, that's why we spend time to do homogeneous transformation. This transformation is, we say that transformation is changing of the coordinate, right? And the purpose of changing such coordinate is to what? To do, helping you to do mathematical calculation. And the purpose of having this mathematical calculation is to helping you to do calculation without using two kinds of operation. You don't need to do addition, subtraction, and multiplication of matrix at the same time. No, you don't. Now you translate it into the homogeneous transformation. Then this 2D coordinate becomes 3D coordinate. It's a little one more degree, but the benefit of it is that the calculation is more easier. It actually just becoming rotational matrix. Everything becomes so. Using this homogeneous transformation, you can combine translation, rotation, orientation, and even including scaling together in one same matrix operation. Then you go back to the chapter 1. We talk about algebra, linear algebra, right? The appendix that we did in week 1. you would put everything into Python and you would be able to calculate. That's the whole purpose of discussion. This is a homogeneous transformation. Okay, that's the whole purpose of doing that. So here we do have different transformation, scaling, okay, dilation, okay, reflection, rotation, shear is a skew, okay, but we are rigid bodies, so this one and this one we don't discuss, okay, but even that you can still come out with metric for doing that, okay, and translation. So now you actually can look at this different effect and different homogeneous representation of them, okay? Okay, so that's that. And then remember you put your rotational metric on the corner here, okay? So this one, because your vector xy, your p is put here, okay? P is a 2 value or 3 value. Here put a 1, okay? And your displacement is put here, okay? 0, 1 is a rotational metric, okay? Displacement vector is put here. Rotational metric is put here, okay? That's your combination of your homogeneous transformation metric. And you are creating a new combined metric A that combine everything. O, okay, A. Okay, so that's the purpose of doing this homogeneous transformation. Okay, and then there are different things you need to look at, okay? So there are different kind of a join. We do have different kind of a join. Revolute join, okay, we draw in this way. Prismatic join, we draw a certain way, okay? And then this right-hand rule. We talk about right-hand rule, okay? 2D link, okay. Okay. So 2D link, we do have two join. Two join, we have a theta 1 here, theta 2 here, and then we have a endpoint here. We also have the displacement D1 and D2, two displacement here, okay? And we are going to look at this one for the coordinates, okay? Let's go two link planary arm, okay? Then two link planary arm means that it's on a surface. This one only provide two-dimensional, okay. I'm sorry, this one indicator, you get out of here, no. It's only provide you the two-dimensional link, okay. Your theta rotate on the plane, theta 2 also rotate on the plane, okay. This is a two link planary arm, okay. Simple model. Okay, and your chain, your open chain, your translation 0 based on frame n will be equals 0 on 1, 1 on 2, 2 on 3, 3 on 4. Okay, it's a multiplication of everybody. This one is the direct kinematics. Okay, you can combine everything together. Okay, that's the benefit of using the homogeneous transform metric. Okay, so you can trace all the way from your endpoint back to your original. And as long as you know about your coordinate with respect to your friend n, you can use the backward translation one by one, one by one, one by one. There's orientation, rotation, and displacement. Orientation, rotation, and displacement. And it go back to these. You can get the overall transformation for everyone. Okay, so that's the purpose of this week's talk. Okay, any question? Any question right here? No? Okay, any question about Python for coding? I know this material you may not have question, but any question about the Python language or coding or assignment? No?
I have a question about the assignment.
Okay, go ahead. Go ahead. I'm okay to discuss.
So with our assignment and like problem one is to model the articulated manipulator using like kinematics. I was just like kind of wondering, isn't that already kind of shown in the PowerPoint, or do you just want us to like make our own version of it?
Let's look at it, okay?
Uh,
So here, this one, okay, let's get the PowerPoint, okay?
mhm.
There's a PowerPoint, okay? Here we do have something, okay? Okay, problem, model the articulated manipulation using kinematic diagram. Write a Python program. Number one, you need to write a Python program, right? To demonstrate the vector V will be rotated after the following rotation. Okay, your Python code calculate the complete rotation matrix from frame 0 to frame 3 using an articulated manipulator with three angles being 15 degrees, 30 degrees, and 60 degrees. Okay, so kinematic diagram, first you need to model the articulated manipulator with a 3D diagram, right? So first thing is that you need to make sure this one is a articulated manipulator. So we draw it, yes, we do draw it here, right? But what's missing here? There's no theta. You need to put theta on, right? But theta is described here, but here we don't have theta, right?
Right, right.
Right. You need to assign theta, and then besides that, so you make it complete and do it. Okay. We do give you some hint, but that doesn't mean that this one is complete. Okay.
Okay.
That's one thing. Second, after you finish that, okay, at this moment we are considering the link is 0, 0, 0. The distance here we all assume 0. So it's kind of like a conceptual robot arm that had no length. Okay, this won't happen. Okay, this won't happen, but this actually is something that is a three cycle, actually is all center the same location here. You know what I'm saying? You know what I'm saying?
Uh-huh.
Otherwise, there should be some displacement, say A here, A here, A here. Your friend should include that, but we don't care about the link right now. We just care about the first one, you do rotate 15 degrees. Second one, you rotate 30 degrees. Third one, you rotate 60 degrees, right? So this vector will be rotated after 30 degrees. What happens? So let's see. That really means that here you do have a coordinate, and this guy actually, let's assume is x, y, z. Okay, and there's a point called 100. Okay, 100 actually is the point over here, right? And you do have the rotation of the frame 0, frame 1, frame 2. You do have 3 frames, you rotate. And then what is the new, you rotate it on here, okay? Rotate with a certain angle. And what is the final location of this vector? Is that okay?
Uh-huh.
So basically you have these 3. So the first one, let's see. The first one actually, let's assume this one, and the theta you define in this way. So you have to assign your theta. So this guy rotates 15 degrees, so it's moved to here, right? Second one, you have another one that's assumed is actually is this one. It rotates for 30 degrees. So this one is, that's assumed that the point already here, right? This one is moved up by 30 degrees. So actually along this G direction, it move up 30 degrees here. And the new location should go to here, right? Is that okay?
Yes.
And
Thank
then
you.
a third one still in here is actually overlap, right? Second one and third one is a 2D plenary. It rotates another 60 degrees, so it actually here. Is that okay?
Yes.
So I'm expecting this point to be okay. I can tell you the answer actually, but you need to model, give me the Python code, okay? it is originally from here. It actually is 100. This guy traveled by 15 degrees to here. Then it moved 90 degrees to here, and it will be here. Is okay?
Uh-huh.
So I'm expecting the final result will be 001. Does that make sense?
Yes.
Okay. But knowing where it is not important. It's how you come up with the Python code to solve it. Okay. And it's welcome to ask questions like this. Okay. This is pretty much welcome if you don't understand the problem. Okay. Key point is that I want you to go through the modeling of this and also knowing about how to apply the math to solve such a problem. At this moment, it's a pseudo problem. There's no link involved. Okay. And later we are going to build more complicated model. Okay. Does that make sense? Any more questions? Any question about the multiple choice one? No? Okay, how about Jay? Any question? If no question, we will be ending here, okay, for the day. Is that okay? Okay, see you next week, okay? See you next week. And let me know if you still have question. Yeah, question? No? Okay, no question. See you next week, okay? And then
Thank you, sir.
Yeah, in the middle, if still have question, you can post me on Facebook, email, whatever. Welcome, okay? Okay, see you. Bye-bye.
Thank you.
Bye-bye.
Bye, sir. Thank you.
Bye-bye.